Thank you guys for today joining my seminar about proximal policy optimization. First of all, we need to know about something about PPO. PPO is one of the algorithm we are using to fine tune LLM, and more on that, it's an reinforcement learning algorithm. And today we will talk about PPO. So what is PPO? PPO is a reinforcement learning algorithm designed to enhance policy optimization by balancing stability and performance, improving upon earlier methods like DQN and TRPO. So this is the algorithm designed to enhance the policy. Policy is the way how we choose action or currently in LLM which you work for the sentence the right the pseudocode is a PPO clip. Actually, PPO and PPO clip and the same. Uh, they are one, but people like to call it with clip and it will be much more correct. Later on, we will talk about this clip. Before understanding TPO, I want to talk about DQN and TRPO first. So DQN or Deep Q network was a breakthrough in reinforcement learning. I remember it was invented in 2015. It was invented in 2015, right? It's a breakthrough because it's changed the way how we focus on the tabular method, like Q learning, and it solved the problem of what do we call it? Discrete action space and discrete action space and discrete state, because sometimes some environment have near infinite state, and they want to break through the problem that need to save a lot of state and action pair by pair, pair to pair into a memory. This algorithm allow agent to learn from state and action. Approach revolutionize the field of enabling learning in complex environment. Currently, the complex environment work not to correct, because right now the complex environment have notified we don't understand what is complex environment. Maybe an environment have infinite state is complex environment, or maybe an environment have near infinite state can be a complex environment. But currently we will use near complex to near infinite to infinite state environment as complex environment. And in the concept and advantage of DQN, the concept behind DQN is approximate the Q-value function using a deep neural network. This approach provides several advantages, including improved learning capability in complex environment. Right now, DQN just solve the problem, like just solve the discrete problem, discrete action problem. Cannot solve continuous action space, because it's quite hard for making an algorithm for tabular method to change into something more complex, like continuous action space. So this is a big problem of DQN because currently in the real world, there not much discrete action space. Not smart, yeah, it's so low. Currently, DQN has been successfully applied to various tasks, demonstrating its effectiveness because of the bucket space and the discretization. They can solve continuous action space, but currently it cannot be like DDPG or deep Q deep Q learning V3 DQ learning V3. If someone wants to try to implement DQN in deep Q network, the pseudocode is on the right of the screen. On the right of the screen, and if you if you can see over here the set YJ. This is equation. This equation is actually Bellman equation, right? It's actually Bellman equation, and if you feel this equation is difficult, just understand as it's mean square rồi. Someone have question about DQN, or we can skip. Okay, to the next one. As I said, DQN has some limitation. Not some, it's a lot of limitation. It's changing the tabular method, right? It's changing the tabular method into a deep Q learning. So actually DQN have a very low instability in training. If someone here try to do DQN in some simple problem like cat pole or mountain car, they will understand that when you train this for a little bit, is the score of the game going up, but instantly it's dropped down. Instantly it's dropped down, and it cannot learn anymore. Like you can I said you can like women. We don't understand how they think, how it's behave, and actually it's very hard to converse an DQN model. Actually, DQN primarily operate based on previous collected data, make it an offline method. This one is offline method, and TRPO and PPO and offline method too. They use value bootstrapping, but currently we don't talk much about value bootstrapping. Maybe for another seminar we can talk about value bootstrapping. This is a very great way to understand how we demonstrate the mathematics behind DQN. Can you can turn on the mic and
Okay. I have a question. So I understand that the main limitations of DQN is that it cannot deal with continuous data.
no continuous action space.
Continuous action space.
We call continuous action space like something we try to what can I say? If you call discrete action space is probability. So the continuous action space is for something like regression, something for like regression, like
Okay.
actual value.
Okay, so it cannot deal with regression problem.
Yes, that's
Okay,
why we that's why we use for because actually just for probability.
okay, okay. Thank you.
Actually, it can deal with this can, but it needs to discretization. Discretization make the regression space into probability space, but it's actually not good. Very not good. It's very bad.
Okay.
Someone have a question? Someone have more question about it? Okay. This part is much more. This part is harder, but actually, it's the main part of. It's the main part. TRPO, the Trust Regional Policy Optimization. This is the pre-PPO. This I call this is pre-PPO because PPO just improved just a little bit of TRPO. This now let's talk about TRPO a little bit. The Trust Region Policy Optimization is um, it's a method in reform learning focused on enhanced stability during training. It's different from DQN. DQN is DQN is instability, but this one is much more stability in training. But it has some problem because of the magnetic behind TRPO. So the training part of TRPO is very very slow and hard to understand. Now this method optimize policy by adjusting with chart region, ensuring that each update step is not too large. We will talk about this later. And the concept of an advantage of TRPO, like I said, it includes improved stability during training compared to previous methods like tabular method like Q table or deep learning method like DQN. By constraining policy update with chart region, is often more reasonable approach to policy optimization. And this stability is crucial in achieving effectiveness and reliable reform learning in effective and reliable reform learning problem. Currently, it's used almost for LM. Yeah, because in robotic field, it's not written. The TRPO and PPO are not too good. It's not too good. Okay, the TRPO, this is the algorithm of TRPO. It's divided into two part. Two part. Okay, let's talk about let's talk about this equation. The theta is the parameter of the model we used to compute. K plus one is the after we update parameter. This is the way how we update the parameter of the model. By we take the azimuth theta of loss of theta k. Theta k is the previous of current current theta and theta not have nothing below it. Below is O is O model parameter, and it have a Lagrange constraint. It have a Lagrange constraint. It's DKL. of theta and theta k, and it needs to smaller or equal sigma. Sigma is the parameter that we will define. So what? Let's talk about let's talk about L L theta k, L theta k, and theta. This is the expected. This is the expected value when we denote when we denote the p theta k as the policy with the parameter theta. Okay, so so let this part, the p theta as divide for p theta k as is actually the differentiation between the old model and the newer model, the newer model, and the AP theta k of SA is actually the surrogate advantage. We call it surrogate advantage because it's actually not the reward. It's the sum of reward uh, reduced by time.
I have a question.
Okay.
So theta k is our current model parameter, and
Yes.
k plus 1 is the next state. So what is just theta? What is theta? Theta.
Uh, Theta is model parameter, not the model.
Okay, model parameter, but like in which state theta k is current state?
Uh,
So which state?
Theta is the old state, like k minus one.
Okay, k minus 1. Okay.
Yeah, we don't call k minus one because when we're changing TRPO or PPO, we don't just use one model. We use several model. Some use currently TRPO and PPO use two model to training, but in some several method of reinforcement learning, maybe that you can use about four model for training, and this one we are only use two. One is for current state, and one for the old state. The old state try to converge to theta k. Theta try to converge to theta k, but the theta k try to converge to the best the best model.
Okay, okay.
Someone here have a question? Any question?
Can you uh, define the big A again? A to the pi of theta k.
A to the a p a pi theta k of SA, right?
Yeah, yeah.
We this is the surrogate advantage, and the surrogate advantage is the reduce sum of the reward. Okay, sorry, I have no pen here.
Okay, so it is
Maybe.
true it if I say that
Oh,
it
okay.
just like add on to the function, like the main part of the function uh we try to like converge p theta to p theta k. It's the main part, right?
Okay, can you ask again?
Okay, so is it true if I say that the big A symbol is just add on to the loss function to make it uh, more advantage in some way, but the main part of the function is the differentiate, right?
No, no. The A is very important. The A is the A part is just like the way how we define how good the model perform in the real world. Okay, so A A is actually we can define as the discrete. Uh, is equal to the sum of the I equal to 0, sorry about the slow pen, to n of the gamma I time reward I. So the gamma is between 0 and 1. The surrogate advantage actually the advantage of when you choose an action in state A to an action in state A, and currently you define which that reward is performed good or bad in current action in current state and in the future too. Yeah, and in the future. This one is we call it surrogate advantage. Yeah, this one is A. It's like when you calculate the differentiation and try to update with and you try to update with gradient, right? So it's equal to A. Uh, sorry, x equal to x minus 2 L uh, LR time delta L in delta theta, right? X, right? So this part is actually the A. It's define how good the model is, and the LR just the differentiation between pi, 2 pi. You can understand like that for simplicity. It can be different uh, in some documentation, but we can define like that for easy understanding. Just turn on the mic and ask directly.
I have one question. Can I ask?
Yes.
Can you explain more about the constraint DKL?
Yeah, we will talk not we currently not talk about the DKL, right? Actually, the DKL part is the constraint of the differentiation, the differentiation of P theta and P theta k. So what is this? Like we said, when you have when you try to learn something, I can set something like that. When you have 10 problems, right? When we have three problem A, B, and C, A, B, and C, right? The problem A currently with the P theta, right? You have about 40% good. The B is about 30% good, 30% good, and the C is about 30% good, right? And the P theta K is about 30, 35, and 35, right? So this part, the theta pi and the theta pi k have a very low DKL. So it can train seamlessly and not have any problem. But if the pi k, the pi theta k have different distribution, like different distribution, like it's about 10, 19, and 10, 95, and 5%, right? So the DKL stop the plus in theta k1 plus 1 to reduce the differentiation between pi theta and pi theta k. It's make the model learn slower, slower, but have more confidence in learning. Do you understand?
Yes, thank you.
Okay, I have question.
Okay.
So like, does it show if KL stands for cool back labor loss, right?
I don't currently. I don't really remember the KL loss.
But it has the same purpose as a cross entropy loss, right?
No, 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 no. Yeah, it's the couple Quebec labeler.
Okay, so it's like a cross entropy loss.
Mm, I
But
don't
it
really remember the KL loss. Yeah, a little bit now. It's have a little bit different, a little bit different. But
okay.
it's not. It's more like log livelihood. It's more log livelihood loss. Yeah, it's more log livelihood. It's log livelihood.
So
Yeah.
we use this loss to update the all the parameter.
No, it's the constraint. It's a constraint. So it's Langarian constraint. Did you see the SD part? Actually Langarian.
Ah, okay.
So at this point, we need to solve the Langarian problem to update the theta k plus one. That's why the TRPO are very hard to compute.
So like the 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 right part of the constraint is the hyperparameter we need to choose, right?
Yeah, the sigma, right?
Okay, this sigma. Okay.
Mm,
So like,
uh,
sorry. So like, in order to update theta k plus one, we need to like iteration calculate loss of theta k with all the previous time step, right?
um, we have a parameter called gamma, right? The gamma is the parameter that reduce in the future time step. Maybe when we set gamma into 0. 0.9, so it's only looking for 10 more step, uh,
Ah,
10 more step in the future. And if this 0.99, it will look for 100 step in the future.
okay. But I asked about the first the update step for the theta k plus one.
Yeah, when we update the theta k plus one, so we need to calculate the advantage. We need to calculate the advantage by collecting all the reward and state into batch and calculate the advantage of S and A, right? And when we have the advantage of S and A, we use it for L theta K and theta.
Okay, so the time complexity is okay, right?
Mm.
Simply put, it's okay. Like we have for loop with k elements in array.
Yeah, currently I'm not trying to understand in the way we talk about the complexity, the big O, right? The big O that is not currently is not really defined because actually the Lagrangian problem have need to solve the duality problem duality problem. When solve duality problem, it's about n four. Yeah, it's about n4. So this this part is actually very very hard to compute because of very big now, very big O. The O is very big. Yeah, just this part is about O and 4. Someone have question?
I have a question. In the A pi theta case, it tells us about uh, it tells us about the difference between the expected reward and the actual reward that we receive.
No, the actual reward and the expected reward are a little bit different. The expected reward is the reward when expected reward the expected reward is actually the reward the is actually the reward when the pi when the pi theta with a s, right, in the as,
Yes.
and this is the thing this is thing model 1, but actually the reward, the actual reward, and the actual reward are defined by environment, but the a pi theta k is sum the sum of reward, sum of reward, and we want the expected reward of the pi theta as try to converge to sum of the reward. Yeah.
I thought we try to make like p theta as to converge to p theta k.
Yeah, but actually it's have not only two this, it's actually not only two model to train. As TRPO, we have one more model to train. It's the
Okay.
expected model.
Okay. So in one update step, we update a lot of model, right? Like k
Yeah,
model,
we have the three model.
three model. Okay.
In some problem like DDPG, we actually need to update five model. So this is the reason why they use PBO in PBO in LLM because the expected model is quite small. It's quite small, and it can use for training the model without changing too much parameter, changing too much hyperparameter.
What are the three models that we update? I think
Yeah,
this
the first one is the first one is the I just call it theta k theta. Okay, actually it's pi, but I just call it theta for easy understanding. The theta k plus one is trying to do the best. Do the best. Okay, the theta is trying to converge to theta k plus one to theta k, and the expected model trying to converge to a pi theta k of s a. These three model.
Okay, so like expected model is try to predict loss given state and action in.
Yeah,
Okay,
actually it's like that.
okay. And then we use expected model to update the theta model,
Yep, that's right.
and the theta k plus one will choose the best of all time step.
Yep. Yeah, and when you see that this is the expected, right?
Okay.
This is the expected.
Yes, okay, I got it.
Someone had more question? Any question? Okay. Oh. So we go into the limitation of TRPO. Actually, TRPO enhance the stability, but it's come with the complexity of computation required, and it's the main reason why they don't use TRPO in real life, because currently reformer learning trying to learn like learn real time, but the TRPO just too complex to learn. This is a pseudocode on the right. So if someone want to implement the TRPO, just take the pseudocode. Currently, this pseudocode is not it's not good, because I found some pseudocode that that's much that's much more correct. But current this one is enough. I think this one is enough. Yeah. And the last part we will talk about PPO, the Proximal Policy Optimization. This is the main part of today. The Proximal Policy Optimization is built upon the advancement of DQN and TRPO, and it's aimed to overcome the limitation while maintaining the stability and performance. PPO has gained a popularity due to this simplified calculation and effectiveness in reformer learning. And we need to talk about we need to talk a little bit about the simplified one calculation of PPO. Actually, PPO are quite similar to it's quite similar to TRPO, but it has a little bit different. The little bit different between is from the clip function. Currently, they don't need to. They still use They still DL diverse, but now the clip function is feeling they feel clip function is much more it's easier to compute and have a better performance. Actually, it's not better performance. It's just easier to compute and work in online situation. Yeah, it's just working better on online situation. And the concept and improvement of PPO is PPO simplify the just region concept introduced by TRPO and make it more computationally feasible. It's optimized the loss function with the simplified region, ensuring the stability during training. It's improved performance and achieve good result in problem with lag state and action space. Currently, we need to talk about the lag state and action space. The lag state and action space here we can understand as of the vocabulary, and action space is actually about vocabulary too. So when we combine it together, we can understand that PPO is one of the best reinforcement learning method for large language model because it solves the problem of discrete action space and discrete action space and discrete state. Very good. Only for discrete action space and discrete state, because when it's come to continuous action space and continuous state, it's a little bit not not that good. Okay, it's changed a little bit, and the different just about the L function, the loss function. When you see over here, it's about this is the loss function, right? It still have the DKL. It still have the DKL, but actually they can remove the DKL into the loss function as a k theta k and theta by set it as mean of the O loss function. This is the O loss function, right? This one, right? This one, and try to clip it into 1 minus epsilon and 1 plus epsilon. Why we want that? Why we want that? Because actually the expected model, the E model, the E model is it's a linear model. It's a linear model. So it can come between the in range minus in range into plus in range, and we understand that when the model has some big parameter push into the gradient descent problem, this can come to a very large change, a very large change in theta, right? That's why when we clip the in range into 1 minus e, 1 minus epsilon and 1 plus epsilon, it can be it can reduce the differentiation between theta k and theta. Someone had question? Any question?
Can you explain more about the clip? Like, how does that work?
Actually, clip is very easy to understand. Do you understand ReLU? right?
Yeah.
The ReLU is actually when it's larger than 0 or smaller than 0, we set it to 0, right? And the cliff is just like that. The cliff is when it's smaller than 1 minus epsilon, it's become epsilon. And when it's larger than epsilon, 1 plus epsilon, it's become 1 plus epsilon. Do you understand?
Yeah. It is less computationally expensive because we don't have to calculate we don't have to update the E model, the expected model.
Yeah, we still need to update the expected model, but we don't need to compute the Langarian problem, right? The Langarian problem is the main cause of computability, because just only the duality problem, đúng không? Right? The duality make it about O and 4. So when we remove the Lagrangian problem, we reduce the complexity of the function, and it still perform good in real world. Any question? Okay. This is the this is the pseudocode of PPO, and we will talk about the way how PPO work. The PPO clip have need PPO. The PPO clip is an offline method, right? So currently, when we work with offline method, we more focus on some way to solve the problem, like Monte Carlo, right? We use Monte Carlos. The Monte Carlos to solve the problem is when we collect a bunch of data, Then we collect the A advantage, and then we update the tree model. Okay. So too easy to understand. We look at the algorithm. Here, when we init the policy parameter theta 0 is the first initiation of theta, right? We need to init the value function parameter is what do we call this? I forgot this symbol called. Yeah, just this symbol. Okay, and we look forever. And we collect the trajectory into a buffer called dk, right? A buffer called dk. And by running the policy pi k equal to pi theta k in the environment, we can compute the reward the reward RT. After we compute the reward RT, we can use it to compute the advantage estimate AT. After compute AT, we can update the policy by maximizing PPO clip objective by this function. Yeah, this one, this over here, this over here is just for DKL. DKL. If we can remove it, but just put it on. It's fine. It's okay. Inside this is a this is the clip PPO clip. This one. And this one we use stochastic gradient descent with ADAM. Sometimes can you batch gradient descent, but stochastic gradient descent is still okay. Stochastic gradient descent is more you on online on some online method, but in this problem maybe it can you ask it can be you ask the way how we train the model. Okay, and then at the last part, we calculate the regression, calculate the value function, theta k plus 1. We can, this one not theta, we can known as this symbol is equal to estimate model. This one is just estimate model. And we compute this forever, just for when we feel comfortable with the with the problem it can solve. That's all. That's PPO. Any question here?
Can you tell me about the function of gradient ascent?
Actually, gradient ascent just it's just like that. When you remember gradient descent, right? The gradient descent is like that.
Okay.
L on H, right? The gradient ascent just change the minus into plus.
Okay. So why don't the author just add the minus sign into the function and use gradient descent, because it's like a common term.
No, it's different. It's not common term, right? If you add minus on the x minus LR on the delta L on delta x, right?
I mean the loss function.
Okay. It's actually though. It's actually this is the way. This is the way.
But like does gradient ascent is gradient ascent is supported in PyTorch or TensorFlow or some framework?
No, it's not in. It's have no. It's have no implementation of gradient ascent on PyTorch or TensorFlow. It's only have gradient descent like ADAM or HGD. Only use gradient descent. That's why we need to add the minus term into into loss function to make it into gradient ascent.
Okay.
Any question? Any question? No, right? Any question here?
Okay, so like PPO in large language model exact the same PPO you talk here, right?
Yeah, it's really like the same. You just change the state and the action of the PPO into input and output of the input and output of the LLM. Yeah, like inputs are the sequence, right? Sequence, and
Okay.
output is the sequence.
Okay. And okay.
Any question here?
Okay, I saw that you mentioned the term just region before, but can you explain more about it? Like, what is the difference between just region in PPO and just region in TRPO?
Okay, the trust region policy optimization. So before we talk about trust region, we need to talk about something more complex. Yeah. So when we talk about what we can talk about trust region and something that easy to demonstrate.
Is it true it just region is expressed by the constraint in the update step in TRPO?
Actually, almost every term in reformer learning just an constraint we put it on almost.
Like, uh can
I
you
just try to find some example for easy demonstrate.
scroll back to the slide of TRPO algorithm?
Yeah, TRPO.
So we only update the theta k plus one with the constraint. So is it constraint define the just region? Just region
Hmm.
for the theta, and we only compute the theta that satisfies the constraint with the theta k.
You can understand like that because TRPO is just an um, GPO. GPO. I forgot the name of the. Yeah, it's a policy optimization problem. So so maybe the trust region just for the DKLA function.
Okay.
Any question?
Can I ask a question that will compare an algorithm that outrange opposite seminar?
What do you want to compare?
Like the core idea of PPO is to restrain the model that uh, it calculates the advantage the and the ratio between the new policy and old policy to help an like to know how to update to the new policy, and it restrains the new policy to not be much different from the old policy, and there is some other method like the tau parameter in DDBG.
Yeah,
uh,
actually, currently the DDPG is focused more on the current reward, but the PPO is focused on advantage. The advantage is different from the current reward, right? Because advantage is for future and reward is for current action.
okay.
So we need to understand that the advantage of PPO are the different term of Q in DDPG.
Okay,
Much more different.
understand.
Q is for mean. Q is for mean, right?
So
And A is for the advantage in the future. So it's like GT, GHT.
the advantage equation is based on Bellman equation. Is it true?
Yes, it's based on Bellman equation.
Okay.
Let's in the advantage equation is like that. It's equal to let me remember. It's just a little bit different than Q. The Q and A is just a little bit different. The Q is plus or minus. I forget it. Let me find. Okay, it's plus the max of A Q S A, right? This is Q. This is Q, and A just minus the Q S T A, and this is A. It's still based on Bellman equation. Bellman equation is key. It's everything for reformal learning. Any question? Okay, thank you for joining my seminar, and the seminar will end here.
Okay, thank you.
Thank you.
Tao muốn nói tiếng Việt bởi vì cái bài này mẹ nó như nhiều cái lý thuyết nó hơi oằn quá.